As discussed in the previous lessons, the railway remains one of the most widespread means of transport globally, with projection indicating a 100% increase in annual passenger load in the coming years. In light of this growth, it is essential to focus on strategies that further enhance energy efficiency and sustainability of the sector. In particular, this lesson will focus our attention on rail vehicles. As we know, if compared to other transport means, trains are already highly energy efficient. The majority of them are electrified and continuously optimized for further improvements. However, much of the research made to improve trains' efficiency is still focused primarily on traction-related areas, neglecting non-traction systems, such as heating, ventilation and air conditioning system 1. Specifically, the energy consumption of the HVAC system is not negligible, accounting for up to 30% of the total energy use of railway coaches. This offers vast opportunities for innovation. With rising energy costs, increased environmental awareness, and greater focus on indoor thermal comfort and air quality, reducing the energy demand of the HVAC system on board is crucial for enhancing the sustainability of the entire railway sector. Additionally, HVAC systems play a vital role in improving passenger experience, which can further drive growth in the railway sector. Despite the recognized influence of HVAC systems on the energy demand of train carriages, few solutions have been introduced to mitigate this impact. This is partially due to the widespread use of static approaches in HVAC system design. These approaches rely on fixed boundary conditions and operating parameters, without considering the real-time operating condition of the train, which limits the understanding of the system dynamics and makes it more challenging to optimize performance. In this framework, it is essential to develop innovative methods to optimize the energy performance of HVAC systems in railway vehicles using dynamic simulations. However, unlike motionless systems, such as buildings, movable ones, such as railway coaches, face variable boundaries and weather conditions. This occurrence makes it more complex to dynamically assess their behavior due to the absence of suitable weather files. For buildings characterized by fixed locations and orientation, gathering this data is relatively straightforward, as weather parameters are well logged for most locations around the world. In contrast, trains are movable and therefore require weather data that is georeferenced, orientation-aware and time-dependent. Unfortunately, these types of dynamic weather files are not commonly available for transportation systems. The approach described in this lesson addresses this issue. It involves the generation of a synthetic weather data file to be used in simulation, tailored specifically for a train and its route. This is possible thanks to a purposely developed mathematical routine that combines non-weather data based on train location and orientation. The resulting innovative weather data file accounts for varying external conditions such as weather changes, train speed and orientation along the entire train journey. This approach enables a realistic representation of external temperatures, solar radiation, wind speeds and other relevant variables at each time step of the simulation. By using these tailored inputs, simulation can more accurately predict heating and cooling loads, and consequently energy consumption under real-world operating conditions. This higher level of accuracy provides a deeper understanding of the factor at play, allowing for more informed decisions that improve sustainability. To demonstrate the effectiveness of this simulation-based methodology for designing energy-efficient trains, we will apply it to a realistic case study. It is important to note that the custom weather data file, which is essential for conducting accurate energy simulations, can only be developed after selecting a specific train and route. In this case study, we focus on an existing middle-distance train operating year-round on a railway route in southern Italy, following a specific schedule. This train and route serve as a reference system for our analysis. To showcase the potential benefits of this methodology, we will apply it to study various retrofit proposals for the selected train and evaluate the impact of these measures on HVAC system energy demand. The specific energy efficiency measures that will be investigated can be grouped in solution to enhance the envelope, consisting in upgrading the existing single glazing and thermal insulation, solution to improve lighting, consisting in replacing existing lights with LED ones, and solution to improve the HVAC systems, such as the adoption of high-efficiency heat pump chiller, the installation of CO2 sensor to adjust ventilation rates based on actual occupancy, reducing unnecessary heating and cooling energy use, or the adoption of free cooling strategy, which involves using outside air for cooling when outdoor conditions are favorable. Turning to the results of this case study, significant energy savings were achieved. For instance, the implementation of CO2 sensors and the installation of a higher efficiency heat pump chiller both resulted in a 35% reduction in annual energy consumption. Energy savings of up to 50% were achieved by combining different solutions and by optimizing the resulting system. On the other hand, it is possible to notice that negligible savings were obtained from improving the carriage's envelope and the lighting system. These results can be then adopted as a guide to determine the best energy efficiency actions to take. It's important to highlight that the selected revamping measures and the related results here presented are highly specific to the particular railway coach and route analyzed. The outcomes are closely tied to the unique condition of the train and the path studied. However, these results are extremely useful as they demonstrate the potential benefits of this methodology, which allows for data-driven decisions based on the actual operation of the train. This same approach can be applied to retrofit other railway carriages on different routes or to optimally design new trains based on their expected operating parameters. As such, it is a powerful tool for enhancing the sustainability of the railway sector. In conclusion, this lesson introduced a simulation-based methodology designed to optimize the energy consumption of railway carriages' heating, ventilation, and air conditioning systems. This approach can be highly valuable in both revamping and designing phases, allowing for understanding energy behavior of carriages in real operating conditions. The flexibility of this methodology makes it a powerful tool for stakeholders in the railway industry, supporting efforts to reduce energy consumption and minimize environmental impact.